Example number 1, we have here a 300 mm pipe connected by a reducer to a 100 mm pipe. Points 1 and 2 are at the same elevation. Okay, point 1, this is point 2. And the energy lost from point 1 to point 2 is equivalent to 20 kilopascal. Compute the pressure at point 2 if the liquid is water. Okay, so we have a given pressure at point 1. So we have pressure here of 200 kilopascal. Pressure 2 is known. We have the discharge. So let's write the given. Discharge Q is 35 liters per second. Pressure 1, that's 200 kilopascal. They are on the same elevation. So the diameter of point 1 is 300 mm and will reduce to 100 mm diameter at point 2. So we're going to compute the pressure at point 2. So given also here is head loss, which is in kilopascal. It is in the unit of pressure. So since what we are going to use in head loss should be in the unit of meter, so this pressure should be converted to its equivalent head. So for letter A, okay, the liquid is water. So let's convert first the head loss to its equivalent head. So as we recall, the pressure is equals to the product of the unit weight of the fluid multiplied by the height for its equivalent pressure head. So let's determine pressure head by dividing the pressure by the unit weight of the liquid. So pressure for the head loss is 20 kilopascal. Okay, so we're referring here to the head loss. So we convert that into head, 9.81 kilonewtons per cubic meters. So kilopascal is kilonewtons per square meter. So our unit for the head loss is in meters. 20 divided by 9.81. That's 2.039 meters. So this is the head loss in meters. Now, using Bernoulli equation, we have here the sum of the energy at point 1 is equals to point 2. But since we have given head loss here, so we have to subtract the head loss on point 1, and it should be equals to the energy at point 2. So energy at point 1, we have the velocity, so velocity head, v squared over 2g, pressure head is P over gamma, P1, plus the elevation head, Z, equals to velocity head at point 2, minus head loss equals to velocity 2 squared over 2g plus pressure at point 2, gamma plus Z2. So it is given here that the elevation at point 1 and 2 are the same. So our elevation head will be equal, so they will be cancelled out. So Rewriting the equation, we have V1 squared over 2G plus P1 over gamma equals to V2 squared over 2G plus P2 over gamma. So what is required here is pressure at point 2. We can now substitute the given values for velocity. For the velocity, we can determine the velocity at point 1 and point 2 by using the given discharge. So the given discharge is 35 liters per second. So we will convert that first to cubic meters per second, just divide it by 1000. That's 0.035 cubic meters per second. Now, we have an equation of discharge equals to area times velocity. So, for us to determine the velocities at point 1 and 2, we can use this formula. So, it means the velocity at point 1 is equals to discharge over area. So, discharge is always equal at point 1 at going to point 2. They are constant. The discharge is always constant. So, here, divide the discharge of 0.035 cubic meters per second by the area, cross-sectional area of point 1. So, area at point 1, that's 300 mm. So, 300 mm diameter, pi d squared over 4. So, pi times the diameter. So, that is in diameter. So, we convert this first to meters. So, 300 mm is 0.3 meters for us to have a consistent unit of meters for the square meter for the area. So, 0.3 meter square divided by 4. Okay, let's solve now. Velocity 0.035 over the area, pi d squared over 4. So that's 0.495 velocity meter per second. Okay, so that's the mean velocity at point 1. At point 2, okay, we will just change the diameter for point 2. So velocity 2 equals to the discharge divided by area at point 2. So same solution, 0.035 cubic meters per second divided by cross-sectional area. So the diameter at point 2 is 100 mm. So that's 0.1. 100 mm is 0.1 meters square divided by 4. Okay. So let's now solve this. Changing this to 0.1. 4.456 meter per second. So yeah. Okay. So the velocity, mean velocity at point 2 is greater than 0.1 because the diameter is smaller. So next, we can now substitute these values at the energy equation. Okay, so I forgot here the head loss. Okay, in the energy equation, we have here head loss minus HL. So let's rewrite that again. V1 squared over 2G plus P2 over gamma minus head loss equals to V2 squared over 2G plus P2 over gamma. Okay, let's substitute. This is P1. Substitute V1 is 0.495 meter per second. We will raise that to 2 divided by 2G, 2 times 9.81 meter per second squared. So, will be added by pressure at point 1 is 200 kilopascal. So, 200 kilonewtons per square meter or kilopascal. divided by the unit weight of the fluid. So we have water, we use 9.81 kilonewtons per cubic meters minus the computed head loss. So 2.039 meters. So all these terms are in meters. It will be equals to velocity at point 2 is 4.456 meter per second, raise that to 2 over 2 times 9.81 meter per second squared, added by pressure 2 plus over 9.81 kilonewtons per cubic meters. Let's simplify the equations. So first, the first term, 0.495 squared divided by 2 times 9.81, 0. Okay, so let's directly add this. 200 over 9.81. So that's 20.3998 meters. So subtracted by 2.039 meters equals to 4.456 square over 2 times 9.81. 1.012 meters plus P2 over 9.81. Okay, so you have 20.3998 meters minus 2.039 minus 1.012 is equals to P2 over 9.81 kilonewtons per cubic meters. So let's solve this. 20.3998, 2.039, and 1.012. That's 17.3488 in meters. So P2 equals to 9.81 kilonewtons per cubic meters. So multiply both sides by 9.81 kilonewtons per cubic meters. We have an answer of 17.3488 times 9.81. That's 170. Okay, 170.192. That's in kilonewton per square meter or kilopascal. So pressure at point 2 is 170.192. Okay, so that's the answer for letter A. If the liquid is water. How about if the liquid is oil with a specific gravity of 0.85? So we have the same solution in letter B. Only that we will just change the unit weight of the liquid. So for letter B, the unit weight of oil is equals to 9.81 times 0.85. That's in kilonewtons per cubic meters. So 9.81 times 0.85, we will use this unit weight, 8.3385 kilonewtons per cubic meters. Okay, so same solution applies here. What will change here are the head loss. So for letter B, liquid is oil. For the liquid, which is oil, we have pressure over unit weight of oil. So that's 20 kilopascal over 8.9 3385 kilonewtons per cubic. So the head loss for oil is 20 divided by 8.3385. 2.3985. 2.3985. That's in meters. So we will use that here on this equation. So in determining the velocity at point 1 and point 2, so the unit weight will not affect the values for our velocity at point 1 and point 2, since the unit weight is not used in computing the velocity. So just applying Q is equals to AV. So we will just have the same answer, given that we will also use discharge of 35 liters per second. So the velocity are the same, so we will not compute that. Let's just rewrite 0.495 meter per second, and the velocity 2 is 4.456 meter per second. So pressure at point 1, same given, that's still 200 kilopascal. And we have a head loss of oil, which is 2.3985 meters. So that's it. Let's apply again. Bernoulli equation. V1 squared over 2G plus P1 over gamma plus Z1 minus the head loss equals to P2 squared over 2G plus P2 over gamma plus Z2, and that's the equation. So Z is cancelled because they are the same in elevation. Next, for velocity 1, substitute 0.495, that's in meter per second raised to 2 over 2 times 9.81 meter per second squared plus P1 200 kilopascal over 9.81. Our unit weight will be unit weight of oil. For the unit weight of oil, we use 8.3385. 8.3385 kilonewtons per cubic meters. Then subtract the head loss, 2.3985. Right? 2.3985. So 2.3985 meters equals to velocity point 2, 4.456 meter per second. We will raise that to 2 over 2 times 9.81 meter per second squared plus P2, which is unknown, over unit weight of oil 8.3385 kilonewtons per cubic meters. Okay, so let's directly solve this equation here. So I will directly solve it using the calculator. On the left hand side of our equation, we have here 200 over 8.3385 minus 2.3985. So the answer is 21.599 meters. Okay, equals to 4.456 square over 2 times 9.81. 1.012 meters equals to P2 over 8.3385. Next, what we will do is subtract 21.599 minus 1.012 equals to P2 over 8.3385 kilonewtons per cubic meters. Okay, let's subtract 21.599 1.012, that's 20.587 meters. Then multiply both sides by 8.3385 so that this denominator will be cancelled out. So we will have 8.3385 kilonewtons per cubic meters times 20.587. 171.665 kilopascal. That's the pressure at point 2 if the liquid is oil. Okay, this is the answer for letter B. And for letter A, we have 170.192 kilopascal. Okay, next problem. Okay, next problem. In this figure, we have the same given dimension of the reducer from 300 mm to 100 mm diameter. Only that we have a given discharge Q of 20 liter per second. So the pressure at point 1 is 100 kilopascal, and at point 2 we have 70 kilopascal. Compute the loss between 1 and 2, head loss. So the required here is the head loss. So let's write down the given. We have pressure at point 1, that's 100 kilopascal. Pressure at point 2, 70 kilopascal. We have the same elevation. So the elevation head will be ignored here. And we have given Q, which is 20 liter per second. Or in cubic meter per second, that's 0.02 cubic meters per second. Okay, applying again the Bernoulli equation. Okay, we have V1 squared over 2G plus P1 over gamma. So let's not include the elevation head because the elevation are the same. Then we subtract that to the head loss, and it will be equals to V2 squared over 2G plus P2 over gamma. So that's our solution for our energy equation. So substitute V1. Let's compute first V1 from the given Q. So Q is equals to AV, or velocity is equals to Q over A. So for velocity, point 1, we have Q, which is 0.02 cubic meters per second divided by the area. So area at point 1, we have diameter of 300 mm. So pi d squared over 4, 0.3 meters squared over 4. So that's equals to 0.02 over area. Zero point 2829 meter per second. And for velocity at point 2, we have 0.02 cubic meters per second divided by the area. Area at point 2, we have diameter of 100 mm. So pi d squared over 4. So that's 2.546 meter per second. Then substitute now all the given. Okay, so before we substitute, let's make the equation. Here, let's isolate the head loss. Okay, either we move it to the left hand side of the equation, and the velocity head and pressure head at point 2, we move that on the left side. So we have v1 squared over 2g plus p1 over gamma minus v2 squared over 2g minus p2 over gamma is equals to the head loss. Okay, so that we can directly solve the head loss. So substitute now the velocity at point 1 is 0.2829 meter per second squared over 2g. 2 times 9.81 uh, meter per second squared plus P1 100 kilopascal or 100 kilonewtons per square meters divided by unit weight. So there's no given liquid here. So let's say in this problem the liquid is water. Okay, there's water in the problem. So water. So we use the unit weight of water 9.81 kilonewtons per cubic meters. Okay, minus velocity 2. So velocity 2.546, or to be consistent we use 4 decimal places. 2.5465. Okay. 2.5465 meter per second squared over 2 times 9.81 meter per second squared minus pressure at point 2 70 kilopascal over 9.81 kilonewtons per cubic meters. That will be equals to the total head loss. Okay, let's directly solve this using our calculator. Squared over 2 times 9.81 plus 100 over 9.81 minus squared over 2 minus 81. Okay, so the total head loss is equals to 2.7317 if we have 4 decimal places in meters. Okay, so that's how we solve a head loss. Next example, we have 150 mm pipeline shown in the figure conducts water from the reservoir and discharge at a lower elevation through a nozzle. So here's the reservoir. Point 1, the water surface on the reservoir is at point 1 and the nozzle is at point 2. So the diameter of the nozzle is 50 mm. The water surface in the reservoir is at elevation 30 meters, while the nozzle is at elevation 0. The total head loss is 13 meters. Compute the discharge at point 2. Okay. So our reference points here are point 1, which is at the water surface. Point 2 is at the opening or at the nozzle. So if we will apply again Bernoulli equation, we have the sum of the velocity head at point 1 plus the pressure head point 2 plus the elevation head subtracted by the head loss, since we have a given head loss here, plus v2 squared over 2G plus P2 over gamma plus Z2. Okay, we are required to determine the discharge in the pipe. So of course, the discharge at the nozzle is the same as the discharge here in the pipe. So let's identify now the velocity head, pressure head, and elevation head present in this figure. So based on the given, we don't have a given pressure here at point 1 and point 2. So we can say that P1 and P2, or the pressure head, is neglected. So next we have elevation head. We have given elevations at point 1 and point 2. So we have values for that. Next, for the velocity head. So for the velocity head at point 1, it is the location where the water surface of the reservoir is. So since this is a reservoir, so the amount of water here is very enormous. The cross-section area here is very big, very large. So if we try to compute the cross-sectional area of this water surface here, that's very high in value. So since our direction of flow is from the reservoir going to the nozzle, so this will be our area, this cross section here, and the velocity is the change in level of water. But again, since considering that our source of water is a reservoir, so the amount of liquid that is traveling here at the nozzle is very small as compared to the total amount of water in the reservoir. So it means that the change in level of water due to the water being transported from the reservoir going to the nozzle is almost negligible. Okay, so therefore the velocity at point 1 is almost zero. So that will be cancelled out. Okay, so because the reservoir is very vast, very large in amount, so the amount of water is that is being reduced in the reservoir is very negligible. Okay, next we have velocity 2. So the velocity 2, when we determine the velocity at point 2, that's when we can determine the discharge. Okay, but last, we can only cancel out the velocity head only when the location of that point is at the reservoir, the liquid surface of a reservoir, or a very large container. Okay, on a very large container. Since here it is not mentioned here the dimension of the reservoir, so it is understood that the reservoir is very big. Okay, that's why we canceled out the velocity. Next, let's substitute the elevation head 30 meters for Z1. The head loss is 13 meters. Velocity 2 unknown, 2 times 9.81 meter per second squared. And the elevation at point 2 is 0. Okay, we can now solve 30 minus 13. That's 17 meters. It is equals to V2 squared over 2 times 9.81 meter per second squared. Multiply both sides by 2 times 9.81, or we can rewrite this as velocity 2 squared is equals to 17 meters by 2 times 9.81 meter per second squared. So the velocity 2 squared is 17 times 2 times 9.81. 333.54 meter squared second squared. Take the square root of both sides. We have V2 is equals to square root of 333.54. Okay, that's 18.263 meter per second. That's the velocity at point 2. Okay, class, based on the given, the 150 mm diameter pipe is not used. It can be used only if point 1 is located within this pipe. That's when we consider the cross-sectional area where we have a diameter of 150 mm. But since our point 1 is at the liquid surface, so and the location is at the reservoir, we didn't consider the cross-sectional area for point 1. And as well as we didn't consider this 150 mm pipe. Okay, now Q is equals to AV. So we have a cross-sectional area. For the nozzle, we have a 50 mm diameter. So pi d squared 50 mm. So we convert that to meter, the 50 mm. We have 0.05 meter squared over 4. Pi d squared over 4 times velocity 18.263 meter per second. So the discharge is pi d squared over 4 multiplied by 18.263. So the discharge is 0.036 in cubic meters per second. That's the discharge, okay, at the nozzle. So actually, the discharge is just the same at any point in the pipe. Okay, that's it. Next problem.